So here we're going to take a step back from talking about work and kinetic energy and talk more specifically about vector operations. And it's going to connect very closely to what we're talking about with work. And we're actually learning about this vector operation so we can use it with work. Now, as you look at this, I want you to be thinking about how it connects back to our discussions with work. Okay, so you can see right here that there's a vector here, vector A, another vector, vector B, and one thing that comes up with vector math is something called a projection. And so you can multiply vector B and vector A in such a way that you're multiplying the projection of vector B on vector A. Now we've talked a little bit about projections when we first learned about vectors. Basically, a projection is what a light shining this way, what the shadow of B would look like. So it would be basically this. So if we multiply this part of B here times A, what we're doing is multiplying the parts of them that are parallel. Okay? And we can find that by multiplying the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. Okay, and if you do this, you're basically finding the projection of B on A and multiplying them together. Okay, and so this is useful for whenever you want to multiply the parallel components of two vectors. Okay, and we call this the dot product. Okay, and so this is one way of finding the dot product, but there's a second way of doing it when we have vectors in unit vector notation. Okay, so that's what I'm going to go ahead and show you next. Okay, so here we have two vectors, and we can kind of draw them out. So vector A is 3i minus 4j, so it's going to be something like this. And vector B is 7i plus 2j, so it's going to be something like this. Okay, and if we find the dot product, we're basically finding the projection of one on the other. So it could look like that, could look like that, and we'd multiply those parallel components together. And as I told you before, we could find the magnitude of A and the magnitude of B and multiply those two things together. But we'd also need to know what this angle was in order to do that, because we'd say by the times the cosine of the angle between them. So we actually have another method that we can use if we multiply all of their components together. Okay, so if we multiply everything together, 3 and 7 is going to make 21, and this is I squared. Okay, and then we can say negative 4j and 7i would be negative 28ij. Okay, and this is called, by the way, as I was saying before, this is called the dot product. And so we multiplied those, then I'll multiply the 4 and the 2, so negative 4j times 2j becomes negative 8j squared, and then 3i and 2j becomes positive 6ij. Okay, so from here we have these weird quantities here, the I squared, the ij, the j squared, and the ij. And so we need to figure out how to simplify those. And the way that we can do that is by going back to the definition of the cross product. So remember, it's the magnitude of the two quantities, A and B, times the cosine of the angle between them. Okay? And so we're going to focus right here on the cosine of the angle between them. Okay? And so the magnitudes of all of these unit vector combinations are either going to be 1 or 0. And the way that we can tell is by thinking about their angles. So I times itself, the angle there is going to be 0, which means it has a cosine of 1. So that's going to go to 1. Okay, I and j, those are perpendicular. I is horizontal while j is vertical, which means that if the angle between those is 90 degrees, the cosine of 90 is 0. So this term turns into 0, it goes away. Okay, for this term right here, the j squared, j is parallel to j, which means it's cosine of 0, which means this turns into 1. And then with the 6ij, those are perpendicular again, so that becomes cosine of 90. So that goes to 0. So we end up with 21 minus 8. And these now, well, these are unitless numbers, I guess, so let me remove that. Okay, and then so 21 minus 8 is going to be 13. So in this case, A dot B was equal to 13. So the dot product of vector A and vector B was 13. So this is basically how parallel they are. Okay. Alright, so to continue, let's do another couple examples and then we'll wrap this video up. Okay, so now we have vectors C and D, and what I'd like you to do is to go ahead and find the dot product of C and D. Find C dot D. Go ahead and do this yourself. Okay, so for C dot D, I'm going to go a little bit quicker this time and show you a little bit of a shortcut. Since we know that I and J are going to give us 0, we don't have to multiply those components. We'll just multiply the ones that are parallel. So 5 and 2 makes 10. I squared, which is just going to be 1, and negative 4 and negative 8 makes positive 32, j squared, which is 1. So C dot D is equal to 42. Okay, so it can get pretty simple there. Alright, and then let's say I wanted to know the angle between vectors C and D. Well, I can use the definition of the dot product. So C dot D is equal to the magnitude of C times the magnitude of D times the cosine of the angle between them. So if I know that this is 42, if I could find the magnitude of C, which is the square root of 5 squared plus 4 squared, and the magnitude of D, which is the square root of 2 squared plus 8 squared, then I could find the angle between them. So this would be the square root of 25 plus 16, or the square root of, sorry, that would be 41, and this would be the square root of 4 plus 64, or the square root of 68. So this would be square root of 41 times the square root of 68 times the cosine of theta, and if you wanted to, you could go ahead and solve this for that angle theta. You could divide those over and then do inverse cosine. Okay, something else I want to mention, so when we do the dot product, we're taking two vectors and multiplying them together in a way that gives us a scalar. So you've taken two vectors and you ended up with a scalar. Okay? And so sometimes this is called the scalar product because we're ending up with a scalar even though we started with the two vectors. Okay? And so let's connect this now back to work. Okay? With work, what we said was a force can only do work when it's parallel to the displacement. So if you have a force that's acting at an angle, only the component of the force that's parallel to the displacement will actually do work. And so doing the dot product can allow us to find work when we have vectors, say in like unit vector notation. And in work, you have a vector displacement and a vector force, and you end up with a scalar, which is work or energy. And so the definition of work, which we kind of have been working with, is that F times displacement, it's actually F dot displacement, is equal to the magnitude of F times the magnitude of the displacement times the cosine of the angle between them. And so we've used this, and we use this in class. We're going to also use this. And so this is kind of like the third definition of work. So we know that we can find work by saying F times X if they're parallel. We can do it by finding the change in kinetic energy, and we can find it by doing the dot product of the force and the displacement. Okay?